Thank you for having me. It's a pleasure to present to you all. So yeah, I'll be talking about generalizable robotic agents through large-scale simulation. And as a teaser as to where we're going, I'll be talking about how we developed Spock, the shortest path Oracle clone. So Spock is an end-to-end trained robotic agent that uses only RGB sensors as input, so no depth, no map, no LiDAR. Spock is trained purely in simulation and works seamlessly in the real world with no real-world adaptation or fine-tuning. We train Spock to imitate heuristic shortest path experts, and this can be done in simulation at large scale with no RL and no human data. And despite being trained to imitate shortest path experts, Spock is proficient at long horizon tasks and is able to exhibit backtracking and error correction behavior. So here's an example of our Spock agent being deployed in the real world, again, without adaptation, to fetch a mug. And you can see its RGB inputs for the navigation and manipulation cameras on the bottom left. So it finds the mug, it explores, and eventually picks it up. Okay, so taking a big step back, let's talk about some motivation. So it's pretty clear that large-scale image, video, and text-based data sets have really been the driver behind all of recent advances in AI. So in the computer vision world, we've went from the ImageNet dataset, which was already quite large at the time, to these Lion 400 million and Lion 5B datasets. And with each step up in size, the capabilities of these models continue to improve. And the question that we really asked was, what does it mean to take this seriously for robotics? And so obviously we're not the first person or the only people to be thinking about this. There's the well-known RT1 paper from Google, where they collected 130,000 episodes using a fleet of 13 robots over 17 months. And there's the more recent OpenX embodiment data set where research labs and many institutions got together and were able to pool 1 million episodes of cross-embodiment data. Both these data sets are awesome, but they suffer from the same problem, and that is simply that they do not scale. If I want to collect another 1 million episodes or another 130,000 for RT1, I need to spend another 17 months doing so. So if we're talking about scale, simulation, or I would claim that simulation is king. It's fast. You can do a lot of interesting things in it. So here's the AI2 Thor simulator from our team. So you can interact. The visual fidelity looks pretty good. And again, it's fast. And obviously, we are not the only people that believe this is a good path forward. There are a ton of different simulators out there. Gibson, Habitat, RL Bench, and many, many more, with many coming every day. So while simulation, I would claim it is king, I would also say that simulators themselves have been a bit of a disappointment. And this is because of a few reasons, one of which is limited object diversity. So the amount of diversity within these simulators is far beyond what we expect in cluttered real-world scenes. And there's also just a lot of limited environment diversity. So, many of these simulators are purely household environments, and they come in only one of a few different indoor flavors. There's also a relatively large sim-to-real gap. This is both sort of in visual fidelity, but also in the physical realism. And this isn't really a criticism of simulators themselves, but because they're fast, they tend to be used really inefficiently. So to solve a simple problem like point goal navigation, we had to train, or other groups had to train, for billions of steps. So to sort of address these different problems, we have a number of contributions. The first, for limited object diversity, is this Objiverse data set. So this is a universe of annotated objects, 800,000, that can be used in simulation. To tackle the problem of limited environment diversity, we introduced ProcThor and Holodeck that allow us to generate an unbounded number of indoor interactive environments using procedural tools and LMMs. And then I will claim that the sim-to-real gap and this inefficiency problem are not real problems when using Spock, but we'll get to there in a bit. So as an overview, we'll be talking about scaling objects, scaling scenes, and then finally Spock. It's fair for me to pick on this AI2 Thor simulator since it's our simulator. It's pretty great. It has 2,000 object instances, 108 categories. You can do a lot of interesting research with that, but that's simply far and away not what we see in the real world, even on a day-to-day basis. If I think of larger data sets of 3D assets, a well-known one, of course, is ShapeNet, has around 50,000 instances from 55 categories, not a huge number of categories. And when you look within the different objects, the variety isn't super huge and the visual fidelity isn't super high. So in comes Objaverse. So this is a universe of annotated 3D objects. And in particular is 800,000 Creative Commons licensed 3D assets that come with annotations. And these objects all come from a variety of different object categories. And these are things that you might want to have for robotics, like furniture and home, but even extend to the sort of slightly more esoteric, so like science and technology type of science fiction sort of world. Within Objaverse, there's a huge amount of variety. There's animated object, rigged objects, and within categories. So for this chair category on the bottom left here, we see that it really ranges from the very photorealistic on the left to the extremely abstract on the right. And here's just another example of an articulated object that might be of use in robotic applications. So now I've claimed that Objaverse is good for robotics. So can we just throw these objects into a simulator? Well, the answer is no. There are many missing critical annotations if we want to do this. For instance, these Objaverse assets don't have any information about scale, object types, whether they're appropriate for homes, or any priors on their placements. So to sort of get around this, in the Spock paper, we introduce Objaverse Home. This is a set of 40,000 additional annotations that we selected for the objects that are most likely to be in or most suitable for indoor environments. And these come with object descriptions, object types, and scale, all the things we need to put these objects into simulators. The next problem that we have using these Objaverse assets is that they don't come with any real sort of unified format, and they're highly unoptimized for use within simulators. When we want to use an object in a simulator, we want it to be relatively lightweight, not be super dense polygonally. So to be able to handle these problems, we introduce this Objathor piece of software that's open source and available that automatically will sort of unify and optimize assets so that they can be used easily within simulation. And even more recently, we introduced this GPT-4V annotation pipeline that lets us now annotate input objects without involving humans at all. So we can sort of close the loop on that pipeline. So here's an example where I asked GPT-4V to annotate a spot robot mesh that we have in Objaverse. And its description is quite nice. This is a quadrupedal robot with yellow legs and a black body featuring articulated legs ending in black feet. I should say also very recently, we've actually annotated over 600,000 of these assets. So these are all available for use. Ping me if you'd like to actually use them. So that was scaling objects. So now we want to scale scenes. So there are a couple different ways, or maybe two main ways traditionally that people have scaled scenes for simulation. One is to manually design the scenes using technical artists. That's what we did for AI2 Thor. Or one can go out into the real world, as in this Habitat Matterport 3D dataset, and scan 3D environments. Both of these approaches are expensive and hard to scale. If I want more assets or more rooms or houses on the left, I have to hire artists. And if I want to have more houses on the right, I need to go out with Matterport cameras and scan more houses. So in comes Proctor. So here we show that we can scale embodied AI by procedurally generating interactive 3D environments. And so the way we do this, again, is procedural. We begin with an environment specification. So this is saying that we want a house that has a bedroom, a bathroom, a kitchen, and a living room. From that, we sample floor plans in 2D. Given a floor plan, we can then sample object placements using inductive biases as to where these objects should be placed. Then we can sample lighting, and finally sample floor, wall, and ceiling materials. And after doing this, we actually have a fully interactive 3D environment in which we can train and evaluate agents. So here's just a small example of the variety of different environments that can be generated with Proctor. Again, this is all procedural, so there are an unboundedly large number of these. And as we show in this Proctor project, scale really matters. As we go from 10 to 100 to 1,000 to training in 10,000 Proctor environments, performance on held out zero-shot evaluation settings for navigation improves dramatically. And this is an observation that we don't just show for one environment or for one task. We show it across a large number of variety of tasks and environments. And we even see that the performance or the gains increase even further if we consider pre-training with Proctor and then fine-tuning on the training data sets for these different evaluation benchmarks. So Proctor plus Objaverse is fast, cheap, and unbounded. Its one downside really is that it's templated, right? So you have to start with a template for what your environment looks like. And this means that I just simply cannot generate something like this language description where I want 3 professors' offices connected to a long hallway with the professor in office 1 being a fan of Star Wars. So in comes holodeck. We replace the procedural aspect with LLMs. And doing this allows us to generate fully interactive environments that look like this. So here we see that there are indeed 3 offices connected by a long hallway. But perhaps even more importantly, because we are leveraging Objaverse, which has an incredible amount of diversity, we're even able to respect that there should be a fan of Star Wars in one of these offices. So there's, again, a huge amount of different and interesting environments that you can generate. So here's an arcade room with a pool table placed in the middle. We can also have a garage with a red sedan and a black bicycle. Again, there's a huge amount of variety, and I don't have time to go over all the details, but humans do like these scenes. They look good, and we're able to show that you can train agents in these holodeck environments and get them to do interesting things. Okay, so that was scaling objects and scaling scenes. Last, I will end with Spock. So the fundamental hypothesis underlying the Spock project is that with enough data and diversity, imitating heuristic experts in simulation can enable real-world navigation and manipulation. And so I've talked quite a lot about data and diversity, so let's jump into imitating experts, heuristic experts in simulation. So one of the huge advantages of using simulators is that they just have a wealth of ground truth data. And that wealth of ground truth data means that it's easy to write planners to do different tasks. So if I want to write a planner to have my agent navigate from one place to another, I can just grab shortest path from a nav mesh inside the environment and have the agent walk along that path. Similarly, if I want the agent to navigate to a particular room, well, I know the layout of the entire environment, so I can just have the agent follow a path to that room. If I want to do manipulation, well, I have the exact object geometry, and I know the exact position of the object in relation to my agent, so I can plan directly to that. If I want to do a scene-aware planning, I know all of the object states and the relationships between all of the objects in the environment, so I can generate a plan where an agent is going to a container closest to the ground. So here the agent walks to one container, realizes that it's the not the highest, it goes to another, and then comes back to the the closest one to the ground. So given that I have all these planners, now I would like to generate data for a bunch of different interesting language condition tasks. And the way that we thought about specifying tasks is by dividing them into behaviors and goal specifications. So here I might have the behavior of navigating to an object, and I'm specifying which object I want the agent to navigate to by, for instance, a type. So you might say navigate to a toolbox. But I might also want the agent to navigate to an affordance. So navigate to the container that can be best used for carrying tools to different locations. Or I might want to navigate to an instance, navigate to the yellow rectangular closed toolbox with black metal strips, or even a relative attribute, so navigate to the largest toolbox. So that was navigation, but of course there are a bunch of other tasks you might want to do. So picking up, fetching, grabbing objects from different rooms and bringing them to different rooms. And then there are some other tasks that don't fall so cleanly within this behavior goal specification sort of definition. So you might have a task like conditional navigation, where if the toolbox is full, find me a cloth bag. Or you might have some interesting exploration tasks or more complex multi-object rearrangement tasks. So given these tasks and these planners, we develop chores. So this is a benchmark and training data set. It's open vocabulary. We generate data from 100,000 houses, from 500 plus object categories. We generate over 10 million training episodes with over 10 million or 100 million training frames. This is all multitasks, and it's using the stretch RE1 agent. And I kind of hinted to it before, but if you look at the stretch RE1 agent that we have sort of generated or have in the real world, we've actually augmented it a bit. So there are two cameras, one of which is facing forward, so that's the navigation camera, and one of which is 90 degrees clockwise for manipulation. So here's an example of a trajectory that we would want to imitate in this chores benchmark. So the agent is trying to find a bowl and grab it. The agent is walking along, and you can see this in the navigation camera. It finally finds a kitchen area. It sees a bowl, walks over to the bowl, and then it rotates itself so the manipulation camera is looking at the object, and then finally rotates its wrist toward the object and grasps it. So now that we have data, we need to actually do some training, and we need a model. So at every step, our agent is going to see the navigation and manipulation images for the current time step along with the goal. We're going to pass these to pre-trained and frozen text and image encoders. The outputs of those will be passed through MLPs into to map everything into a shared embedding space. And all of these output tokens in the shared embedding space, along with the CLS token, are passed to a transformer or encoder. And we consider the output from the CLS token to be a sort of goal-conditioned visual representation for the agent's time or observations at time step T. Of course, we want to reason over time, so we'll take that representation and pass it along with all the previous observations or representations to a transformer decoder. And here it's causal because the agent should not be able to see into the future. And for each token or each embedding we get out of the decoder, we then predict a single action, which we then use for imitation. Actually, training this agent does come with a lot of interesting technical challenges. So we might have very long episodes, up to 1,000 steps. So we end up training on these sort of randomly selected sliding windows. And then when we actually deploy the agent, we let it see the entire trajectory. And this actually ends up working quite well. So to summarize, we train on these shortest paths. And despite training on these shortest paths, we get agents that are able to explore and backtrack and exhibit interesting behavior when deployed. We find that the agent or Spock understands spatial relationships. So here is an example where it's navigating to the highest fruit in the kitchen. So it sort of walked past an initial apple, sees some banana that's low, and then comes back to the apple, which is higher. And it performs interesting task-specific behavior. So here's looking for a computer on a sofa. It ignored the initial sofa it saw because there was no computer, then finds this laptop on a sofa. And then finally, we want to, or we would like to show that we actually can enable things in the real world. So here's an example of our agent working in our robotic lab, where it's attempting to fetch an apple. And again, you can see the agent's RGB observations on the bottom right. It explores, finds the apple, and manages eventually to grasp it. Here's a bit of a fun failure case. So the agent is trying to pick up a houseplant. It initially rotates its wrist. The wrist gets stuck. It corrects for that, eventually raises its arm, rotates the wrist so it's aligned with the object, reaches out. It then misses the object, rotates its wrist again, and then actually pulls the plant out of the pot, which is, maybe correct from its perspective, but not correct from ours. We run a significant number of, or a non-trivial number of real-world trials to get some good quantitative numbers. We see that this does work in the real world across a variety of different language condition tasks. And we run a number of ablations. And so from these, we see that really scale, the object diversity and house diversity, the context length that we feed in during training, and the visual encoder, especially using bigger visual encoders, are all really critical for performance. And the architecture that we end up using, this transformer architecture, is important as well. Here, the visual encoder, I just want to stress, is extremely important, having this pre-trained for things to work in the real world. As a failure case, we see that accurate object detection is a large issue. If we give our agent sort of ground truth detections during evaluation, it performs a lot better across all tasks, essentially. And this trend even works in the real world, where if we give our agent open vocabulary object detections from pre-trained models, like this DEDIC model, performance jumps up quite a lot. So we're over 80% for open vocabulary object navigation. So to summarize, here we introduce Spock, the shortest path Oracle clone. This is an agent that's trained end-to-end and is able and uses only RGB observations. It's trained in simulation to imitate heuristic experts, and nonetheless works in the real world and is proficient at long horizon tasks. I don't want to end without sort of marking some additional future or additional progress we've had in 2024. So we introduced polyformers. So we really cracked the code in being able to use transformers with RL for training these sort of long horizon tasks. We get really masterful performance by doing this, highly recommended. And we've also introduced MOMO. So this is a family of open state-of-the-art multimodal models that are actually able to point. So they can ground what they're trying to sort of respond with points in the image. And this opens a lot of interesting applications for robotics. So of course, none of this was done by just me. There's a huge number of different collaborators and contributors and co-authors, and I thank them all. And I'll just end, and feel free to ask questions while this is going on, with a video that shows us using Momo in a robotic application to do some interesting things. So thank you very much.
Thank you, Luca. All right. Any questions for Luca? Yes.
Or did they directly transfer the same policy into the real world, or did they have some sort of
The question was, which last one were you doing? Mobile? Or the RL one?
one training?
Okay, for the last work training proctor, did you directly transfer the policy without any fine tuning and send through?
Yes, so we do no real world fine tuning. Everything works in real sort of right off the bat. The key contributors to this are using these big pre-trained visual encoders. So these are really incredible. And we also do a huge amount of sort of training time augmentation. So we apply pretty aggressive augmentation to the videos the agent sees. And we find if we just do these two things, it just works. We don't have to do anything special to make the agents work in the real world.
Hey, hi, Luca. Thank you for the talk. So you talked about all these new data sets, and you also talked about the importance of these neural models, right? You talked about GRUs or encoder layers of a transformer. So how did you guys decide about the architecture of these encoder layers? Because there are so many parameters, right? And now since you have a new data set, actually, on addition to that, extra question can be, so now since you have new data sets, do you think like using tools like neural architecture search or those kind of tools would help you to come up with better architecture, right, to get better performance?
Okay, so I think I got both of the questions. I guess starting with the neural architecture search question, I think definitely this could be a good way to improve the performance. I don't think we really understand what are great architectures for these types of models. I think the big problem there is that there isn't a great proxy for validation set performance when deployed that we have at the moment. So we really need to take models and actually deploy them in sort of simulated environments, which can be quite slow to evaluate the performance. And just looking at sort of the validation loss is not sufficient. So if you want to do neural architecture search, the sort of the loop of searching is going to be really slow, but I think that is an exciting direction. As to the other question, how did we choose the architecture that we went with? So we prior to this project, sort of all the work we've been doing is with sort of GRUs and standard LSTMs and all these recurrent models. I think what we saw is that these transformers are really, in other domains, the model to go with when you have enough data. And so we decided to experiment with a couple of different architectures. I mean, we have ablations using GRUs. Those work reasonably well, but you just are able to get a little bit more from large scale data if you're using these sort of transformer style architectures.
But like even there are state space model, right? That AI Lab has come up with. I don't know even if those kind of models will make sense.
I think there's like I said, I think there's a really exciting sort of space to try and play around with these different models. I think my general intuition though is that data is more important, and that if you have good data, the models may be like a few points between each other, but if you have bad data, you're going to lose a lot.
Makes sense. Thank you.
Yep.
All right. Maybe one more question.
Okay, thank you for your wonderful presentation. And I noticed that for the scene generation part, your work can generate a very realistic and very impressive static scenarios. So do you consider about the dynamic object generation?
So
if
the seat. Oh, sorry. Go on.
As we all know, the dynamic objects are always impact the performance of our robotics. So I want to know more about this part. Thank you.
Got it. Yeah. So actually, all of the scenes that we generated are dynamic in the sense that they are physically sort of interactable. You can pick up objects, throw them, move them. What they don't have is sort of those, especially with the Objaverse objects, all those interesting like articulations or like soft body dynamics or anything like this. At the moment, that I think is a very hard problem to solve. We need the simulators to be fast, and you can more or less get this to be the case with rigid bodies, if you're sort of smart about how you handle manipulation and all of this. But it's extremely hard if you go to, again, like soft bodies or liquids or things like, or more complicated articulations. So at the moment, I think I'm hoping to get everything we can get out of rigid bodies, and then we can move on to the harder problems in the next year or two.
All right. Thank you so much, Luca, for being here. I know it's very late for you too, but thank you for coming and thank you for the talk.
Thank you.